Hello, my name is Bernie McConnell and I work for the Sea Mammal Research Unit Instrumentation Group in the University of St Andrews, and my aim just now is to present a small sample of technological innovations within our instrumentation group with a view to exploring synergies with other folk in the MASTS community. Before I get onto our work, I want to mention a couple of bits of other technological innovation within SMRU in general. The first is the use of the development of acoustic deterrent devices which deter animals away from other areas of danger or from fish farms. The main characteristic, the requirement of these devices, of course, is that they only affect the target species and do not contribute to general noise pollution in the sea and affect other species. Before we get on to tagging animals and true telemetry, there's two types of acoustic monitoring that goes on. I'd like to mention the first is by Doug Gillespie, and for those animals that vocalise, his array of hydrophones can detect and hear porpoises swimming around underwater turbine in the Pentland Firth. For those animals that don't vocalise, Gordon Hastie has used active sonar, which is like underwater radar, to monitor the activity of non-vocalising grey seals with a range of about 50 metres around a tidal turbine in Strangford Loch. Now, the Sea Mammal Research Unit Instrumentation Group, we've been around 25 years or so. There's 10 or so of us just now, engineers and biologists, and we develop, use and sell to other collaborators from the Antarctic to the Antarctic a variety of electronic tagging systems. And there's 6 things I would like to describe about our activities. First of all, our preoccupation with low energy operation of our devices. There's only so much energy we can carry in terms of battery and we can generate in terms of harvesting systems, and it's got to be used cannily. The collection and the processing and the transmission of data consume energy. These are minimised by use of low power hardware architecture in energy efficient software to the nth degree. Mechanical design expertise is essential if our tags are going to remain small, pressure-proof, hydrodynamically low drag and securely attach the animal. And we have thus developed expertise in CAD 3D printing, encapsulation in epoxy resin and the ability to test these devices in pressure testing facilities. A variety of sensors can be attached to our tags, not all at once, and I'm not going to go through them all one by one, but I'd like to pinpoint 2. The first is the use of near-infrared spectroscopy, principally by my colleague Chris McKnight, and this is a non-invasive way of looking at the oxygenation status of arterial blood in marine mammals, and from this we can look at the behavioural control of blood flow and oxygen distribution in an animal in relation to its dive physiology and its foraging, and here it's being applied to marine mammals and to breath hold divers. The second sensor, which is a compound sensor, monitors the body condition of an animal, in this case northern elephant seals. And as they eat, they store their energy in blubber and they become more buoyant. The animals carry out occasionally things called drift dives, where they're not actually actively finning up or down, and the rate at which they ascend or descend is a proxy for body condition. And here we've got the tag doing these complicated calculations and looking at the changes in an animal's condition over a period of 6 months. The data somehow has to be brought home through a variety of mechanisms. Argos satellite system has been the traditional workforce, but for those animals that occasionally, it could even be once a day or once a month, come near shore, we use the mobile phone system for relaying data called GSM. We're also using Iridium satellite systems and dedicated UHF receiving stations, and we have considered data sharing, which I'm happy to go into later. The data that we collect is complex and multidimensional, and if we're going to make sense of it, which we have developed our own visualization system called MAMVIS, And what we see here is a view looking down into the Murray Firth, and the land next to is Rattray Head, and from the south is kind of a seal is swimming, where you can see individual dives it's feeding or is at, following the seabed, and the marker, I'll try to mark it here, just there, shows when we've detected feeding activity through an accelerometer which detects head jerk movements that are associated with feeding. The points that I'd like to consider in this very, very brief introduction here, there's 4 of them. How do we foster innovation? Because it's easy to stifle it. 4 points. First of all, technical innovation often straddles the contrasting cultures and demands of academic endeavour and commercial enterprise, and finding the right balance between these 2 forces, these 2 cultures, is far from easy, but it is essential. The second point is engineering excellence is fundamental to innovation, yet qualified engineers are often regarded as support to their academic colleagues, and their intellectual input must be acknowledged, and meaningful career structures must be available to them as well. Lip service is often paid to the value of multidisciplinary work, yet funding streams and academic structures may undermine such cross-fertilisation. And the final point I'd like to make is that technological innovation may be carried out often in isolation from fellow engineers and users, and not all academic institutions have a supporting department of engineering behind them. So how can MASTS provide this support and facilitate networking between engineers and also externally with industry? And that's it. Thank you very much.
This is a whistle-stop tour of methods of dealing with availability bias on digital aerial surveys. There are 3 kinds of methods: correction factor methods, mark recapture-like methods, and a variant of this mark recapture-like methods in which you don't have to know what the recaptures were. So onto the correction factor methods, the simplest of which is when animals are in view, so available to the camera or the digital device, only for an instant, that is for a very short time compared to their availability cycle. Then there's a real easy way of getting an unbiased estimate. This number here, n hat subscript a, is the number that you estimate from your survey, which is just the number of animals that were available to be seen. This number here is obtained from somewhere else. It's the average proportion of time animals are available. If you take the ratio of these 2 numbers, you get an unbiased estimate of the number of animals that were there, so including the unavailable ones. So it's real simple. The disadvantage, though, is that getting this p-hat is difficult, and in particular for getting the p-hat that's appropriate for the time that you survey in the place that you survey can be difficult, because typically it's obtained from tagging animals, for example. What if they aren't in view for just an instant? So I've compared 2 scenarios here. This is a camera, this is time or forward distance, and this one has a very narrow field of view in the forward distance. So animals are available effectively instantaneously here. This is the dive cycle of an animal. Yeah, it's unavailable, unavailable, available. So with a very short, narrow window like this, animals can only be available once, and the probability that they're available is just the proportion of time that they're up. This scenario where you have a wide window, so that so it's not instantaneous, animals can be available frequently, then clearly the probability of an animal being available is substantially bigger than the probability that it's available in a tiny window, which is the probability that it's available, average proportion of time it's available. So things get more complicated if your survey is not instantaneous. And if it isn't instantaneous, then that simple equation I showed you, the estimator out of that is a positively biased estimate of abundance. And in order to make it unbiased, you've got to estimate not just the proportion of time an animal is available, but you've got to estimate the availability process. And that's because you could have 2 animals that are available for 50% of the time, say, one available very frequently and then unavailable frequently, and the other available infrequently but for a long time. And the one that's available frequently will tend to have a higher detection probability than the other one. So life gets more complicated if you have a non-instantaneous window. On to mark recapture-like methods. So here's a survey in which you have two cameras on a plane, one surveying this first grey strip, this other surveying the second grey strip, and they're separated by some time lag. So for this being mark recapture-like method, you've got to be able to identify recaptures, which in this context is resightings of the same animal. That method has a few catches. The first is that if this lag is very short, then you don't correct for availability bias. And think of the case where the lag is 0, so this band is on top of this band. Then you're only estimating the available animals, not those that weren't available. So you want to make the lag long, but the longer you make the lag, the more difficult it is to identify resightings because animals have moved. And also long lags make resightings less likely, not just more difficult to estimate, because the longer the lag, the more likely it is that the animals that were available first time have gone out of the strip by the time the second camera comes round. And then if you have a narrow strip width, as is typical of digital devices compared to humans, this problem of long lags gets worse. So the mark recapture method has its problems. On to the last method, which is mark recapture method where you don't have to know recaptures. So if you don't know recaptures, how do you get the information on availability out? Well, here diagrammatically is the camera 1 is the dots, this is time from left to right, camera 2 is the triangles, and some of these will be recaptures and some of them not. And the amount of clustering is informative about the amount of recaptures that happened here without having to identify which recaptures they were. And there are two approaches to this, one called Latent capture history enumeration, which is a variant or generalization of a method that Lex Hebe came up with for a scan survey long ago. And the other is a cluster capture recapture method. Both do similar sorts of things, neither require recaptures. And providing your cameras are separated by enough lag that the availability of an animal for one camera is independent of the availability of another, you can estimate abundance without knowing anything about movement or the availability process. So you don't have to estimate that P parameter at all, and you don't need to know the recaptures. For shorter lags, you have to estimate more things and life becomes more difficult. That's it. Whistle stop tour over.
Hello, my name is Paul Fernandes and I'm a fisheries scientist at the University of Aberdeen. I've been applying marine technology to the study of fish and fisheries for over 30 years, 20 years in government research labs and for the last 10 years in academia. In this talk I'm going to introduce the Smartrawl, which is an idea we have been developing with funding from Fisheries Innovation Scotland, which is supported by the Scottish Government and others such as the Scottish Fishermen's Federation and Sainsbury's. The problem that Smartrawl addresses is discards and bycatch in bottom trawls, the fishes that bring us common species such as cod and haddock. Discards are that part of the catch that are returned to the sea, dead or alive, and are distinguished from bycatch by having commercial value and subject to management. A recent review for the United Nations FAO found that trawling accounts for 46% of global discards. Now, traditionally, fishermen would discard small, undersized or juvenile fish. But over time, this has become less of a problem due to increases in the mesh sizes of trawls. However, discards of adult fish, which was unheard of for decades, suddenly started to increase and became a significant problem in the last 20 years, essentially since the advent of improved control and compliance measures, which no longer allowed fishermen to land fish illegally, notably the registration of buyers and sellers in 2005. And you can read more about that in my 2011 paper. Now, this led to the European discard ban, also known as the landings obligation, which was introduced in 2015. However, recent evidence from the European Fisheries Control Agency has indicated that this ban has been ineffective in the North Sea. Essentially, fishermen have no means to select the fish they have quota for, hence the idea behind Smartrawl. Now here we have a typical demersal trawl. On the left, at the mouth of the trawl, you have the ground gear in grey, which protects the foot rope and weighs the trawl down. We have the floats, here in orange, to open the trawl vertically, and the lines or the sweeps, which lead to the trawl doors, which spread the trawl horizontally. The fish are then swept into the net and caught in the cod end at the opposite end in red, and leading up to the cod end is a long piece called the extension in blue. Now here is a photograph of a scale model trawl in a flume tank in Canada, which we visited last year to test some of our prototypes. And you can see some of these features in it, notably the floats at the top of the headline. Now it's in the extension that we make the trawl smart. So we're now going to focus on that area. So inside the extension are two major components of the Smartrawl. On the right-hand side is the gate, which can be opened or closed to release or retain fish respectively. On the left-hand side is a stereo camera system with an artificial intelligence computer to identify fish and size them as they go by. And this sends a message to a controller which opens or closes the gate. So the idea is when the camera system identifies a species of size of fish that is not wanted, it sends a signal to the controller to open the gate, and the fish are then released back out to sea alive. Whereas if the camera system identifies a species or size of fish that is wanted, it sends a signal to the controller to close the gate, and the fish are retained into the cod end and caught. And so far we've been through 4 phases of development. In the first phase, a feasibility study, we used an existing stereo camera from a similar system from Norway called Deep Vision. However, this system would be too cumbersome for the demersal fishing fleet, so we developed our own stereo camera system. This was developed in phase 2. The stereo camera system consists of 2 stereo cameras, 2 LED lights, a controller, a basic single board computer, and enough batteries to run for 6 to 8 hours, which means that there are no cables running to the system. It's completely autonomous. We then had to build a frame for it to be deployed into the extension of the trawl, and you can see them stitching the frame into the extension on the left on the quayside here. We then deployed it at sea on a North Sea fishing trawler. And here you're now seeing an example of the 200,000 images that we have collected to date. And what you see is the system operating in real time, collecting images at a rate of 2 per second. And this is important data to determine exactly how quickly the gate would need to operate, depending on how quickly the species and sizes go by. We then had a short phase of development funded by the Scottish Government, adding communication via an underwater modem. The idea is to take the image pairs, detect fish with some artificial intelligence algorithms, size the fish with the stereo, transfer that information to an acoustic transmitter which translates the size into an acoustic signal, and send that up to 600 meters in the water to a receiver which transfers the information back again to a laptop on a PC on the bridge which displays the fish size. In this, an incremental phase, we develop the individual components, and we now need to put them all together. We are now in phase 3, where we are developing a gate for the system, and unfortunately I can't say much about that as it's pending a patent application. Future phases will incorporate the last major step to introduce species recognition of the fish in the images, capitalizing on various developments in artificial intelligence to fish image recognition. So that is our vision for Smartrawl, an innovation that will not only improve the sustainable management of fisheries, but also help to protect the ocean's biodiversity by avoiding the unnecessary bycatch of marine animals that are of no commercial interest, but of significant environmental concern.